All right, let's get right into it. Today, we are digging into a really fascinating paper from March 2024. It's called From Data Statistics to Feature Geometry. And honestly, it flips the script on how we thought AI models learn and organize information. So yeah, let's dive in.
So it all boils down to this one massive fundamental question. You've got an AI, like a large language model, that knows about practically everything. Shakespeare, quantum physics, the latest cat memes, you name it. But how on earth does it manage to pack a near infinite library of concepts into a totally finite number of neurons? It just seems impossible, doesn't it?
Well, the answer, or at least a big part of it, is this wild idea called superposition. The best way to think about it is like a brilliant packing trick. Imagine you have a tiny backpack, but need to pack for a trip around the world. The AI takes all these different concepts, we'll call them features, and just cleverly overlaps them inside its limited neural space. It's how it represents way more ideas than it technically has neurons to store them in.
Okay, so for the longest time, the folks who study this stuff had a kind of standard theory for how this whole packing trick was supposed to work. Let's just call it the standard picture. The old school thinking went something like this. When you cram all these features together, they're going to interfere with each other. It's unavoidable. And this interference was always seen as a messy side effect, just garbled random noise. So the AI's whole job was to arrange things to make that noise as quiet as possible and then just filter out whatever was left over.
But here's where things get interesting. When we started to actually peek inside our modern powerful AI models, what we were seeing, well, it just didn't add up. This theory of random, messy noise just didn't fit. There was a real mystery brewing.
On the one hand, you have the standard theory, which pretty much assumes that features are all separate and unrelated. Like the concept of an apple has nothing to do with the concept of liberty, right? But on the other hand, in the real world, these models are chock full of features that are obviously related, like king and queen or hot and cold. You get the idea. And instead of seeing random noise, we were seeing these beautiful, highly organized patterns. Concepts were clustering together in ways that made perfect sense, even forming these weirdly elegant cyclical shapes.
And that right there is the big puzzle. I mean, think about it. If the interference between ideas is just random junk that the AI is trying to throw away, why on earth would it produce such elegant, meaningful geometry inside the model? The old theory, it just had no answer.
And this is where the paper we're talking about comes in and just blows the whole thing wide open. It suggests that maybe, just maybe, we've been thinking about interference all wrong.
The key idea, right from the paper itself, is this. The authors are saying that when features are related, their interference isn't noise at all. It's constructive. The model isn't trying to get rid of it, it's actively using it to figure out the relationships between concepts. So here's the kicker. Interference isn't a bug, it's a feature.
Now, you can't just make a huge claim like that without backing it up, right? Of course not. So the researchers set up this really clever, controlled experiment to put their theory to the test. They called it BOWS.
So here's what they did. They took real text from the internet, which is obviously full of words that are related to each other. They fed it into a pretty simple model. It's called a bag of words model, which basically just counts how often words appear. And they told it to use superposition to encode all this text. And the result? Get this. The model didn't try to shove related concepts away from each other to minimize noise. No, it did the exact opposite. It naturally pulled them together, using the patterns of how they appeared together to build these structured, geometric shapes.
So what this experiment showed is that we have a totally new and, honestly, a much more beautiful way of understanding how these models organize knowledge.
Right, so just to be super clear, the old way of thinking was all about arranging concepts to minimize that messy interference because you thought it was just noise. But the new view, the breakthrough idea, is that features are arranged to actually use that interference. The AI is leveraging the overlap between related ideas to build this incredibly rich internal map of how everything is connected. And what's so cool is that this one little shift in perspective suddenly makes everything click. All those mysteries we saw before, they just dissolve. It explains why we see semantic clusters, all the royal family words hanging out together. It explains those weirdly beautiful cyclical structures people were finding. It all comes down to the model using constructive interference to organize the world based on how often things show up together. Okay, so you might be thinking, this is cool for AI researchers, but why does it matter to me? Well, it's a huge deal because it completely changes how we should be thinking about what's actually going on inside an AI's so-called brain. Here's the bottom line.
We're moving away from this chaotic picture of an AI just fighting against a sea of random noise. Instead, we can now see it as something more like a geometer, methodically and elegantly building a complex geometry of meaning, where the actual distances and angles between concepts represent how they relate in the real world.
And that brings us to one last kind of mind-bending thought to leave you with. For years, the core assumption was that interference was just noise, a problem to be solved. This paper shows it's actually a powerful tool for organizing everything. And it really makes you wonder, what other fundamental ideas we take for granted about how AI works might be just as wrong?